Hello everyone, myself Dr. Mohit. In this video, we will learn how computers and calculators store real numbers using fixed point and floating point representations. First, we understand why we need spatial representations for real numbers. This is the set of real numbers. This set of real numbers includes integers, fractions, irrational numbers like root 2 pi, and repeating decimals such as 0.333. Okay, so many real numbers such as pi or 1 by 3 have infinitely many digits. For example, pi is 3.14159265 and so on. It has infinitely many digits. So in real number system, our real number may have infinitely many digits. Okay. However, a computer or calculator has finite memory, so it can store only a finite number of digits. So the key question is, how do we store real numbers with infinitely many digits on a device with finite memory? Answer is, we store close approximations of real numbers with infinitely many digits using the ways called fixed point and floating point representations. In fixed point representation of real numbers, the position of decimal point is fixed, that is, number of digits after the decimal point is decided in advance and fixed. For example, in a 5-digit decimal fixed point system, if 3-digit space is used for integer part and 2-digit space is used for fractional part, decimal point is fixed, means it never moves. Then how to store a real number in this system? So we discuss here some examples. First is real number 5. In real number 5, integer part is 5 and fractional part is 0. So integer part 5 is stored as 005 and fractional part will be 00. 2.6. Here integer part is 2, so it is stored as plus 002.60. Same for 0.75. And if we talk about 12.356, here integer part is 12, so we it is stored as 012 point. Here we have 3 digits for fractional part. So but we have 2-digit space for fractional part, so we round off this fractional part to 2 digits. So instead of storing 356, it is stored as 36. For minus 3.14, it is stored as minus 003.14. So in a 5-digit decimal fixed point system, smallest number will be minus 99999 and largest number will be plus 99999. Because there are 5 spaces for digits here in this system, and each space has 10 possibilities of digits. Digits may be from 0 to 9, means 0, 1, 2, 3 up to 9. So there are 10 possibilities for each space. So 10 possibility for this one and 10 possibilities for this one, 10. So total possibilities are 10 raised to the power 5. So total number of exactly representable real numbers is 10 raised to the power 5, in which smallest number will be minus 999.99 and largest number will be triple nine plus triple 9.99. Now question is, why do we need floating point representation instead of fixed point representation? Consider the very small number which is 0.000000345. Okay, very small number. In a 5-digit fixed point system, integer part of this number, which is 0, is stored as 000, and two fractional digits are stored as 00. So this number is stored as 0. It cannot be stored accurately because this is a non-zero number, but stored number is 0. If we move this decimal point from here to here, means before 3, and use some use 4-digit space for significant digits, means 3450, and 1-digit space for exponent. So after moving this decimal point, we can write this number as 0.345 multiplied with 10 raised to the power minus 5. Okay, so now you can see here. So this is the significant part. Okay, it is stored as 0.3450 and exponent is stored as minus 5. Okay, so this number is no longer 0 now. This idea is called floating point representation because we are moving the decimal point from one place to other place. Decimal point is not fixed. Here we are floating the decimal point to accommodate the number, real number. So now consider the very large number, that is 345000. So now question is, can this number be stored in 5-digit decimal fixed point system? So answer is no, because this number is greater than 999.99, which is the largest number to be stored in the 5-digit decimal fixed point system discussed in previous slide. So we cannot store this large number as a fixed point representation. Okay. However, using floating point representation means if we write this number, we float the decimal point from here to here, so it can be written as 0.345 multiplied with 10 raised to the power 6. Okay, so this number can be written now 0.3450 10 raised multiplied with 10 raised to the power 6. Hence, a fixed point system cannot represent very small numbers and very large numbers using limited memory. So we represent numbers in floating point form as plus minus m multiplied with 10 raised to the power e, where m is the significant part of the number and e is exponent. Floating point representation of real numbers. Floating point representation is a way to store real numbers in which decimal point is allowed to float. Means it can move to represent number of different sizes. In decimal floating point form, a real number can be written as r equal to plus minus 0.d1, d2, d3 and so on multiplied with 10 raised to the power e. In general, real number can be written as minus 1 raised to the power s multiplied with 0.d1, d2, d3 and so on multiplied with b raised to the power e. Now, what is s here? So s is a sign indicator. S is 0 for positive numbers and it is 1 for negative numbers. B is the base or radix. It is always greater than 1. For some devices, it may be 2, it may be 8, it may be 10 or 16. Here, this part 0.d1, d2, d3 is denoted as M and it is called mantissa. Mantissa is always greater than or equal to 0 and less than 1. The digits D1, D2, D3 and so on, DIs belong to this set 0, 1, 2 up to B minus 1. If B is 2, then DI's values will be 0 or 1. If B is 10, then DI's will be 0, 1 up to 9. Here is called the exponent and E is always an integer. For scientific calculators, base B is 10. So I have told you that DI depends on base. So DI will be 0, 1, 2, 3 up to 9. And for computers, base is 2. So digits are 0 and 1. So these digits are called decimal digits and digits 0, 1 for computers are called binary digits called bits. This representation, this floating point representation is called normalized floating point representation if d1 is not equal to 0. Here are some examples of floating point representation. So if real number is 5.369, so floating point representation is plus. So this point is moved here. Okay. So now it is now 0.5369 and as decimal point moves, so we need to take exponent also here. So 10 raised to the power 1. So this real number can be written as minus 1 raised to the power 0. S is 0 here because real number is positive and this is a significant part of this real number called mantissa. It is 0.5369 and 10 raised to the 1. Exponent is 1 here and it is for base 10. So this real number here, this is the negative real number. So S is 1 here. So it can be written as minus 1 raised to the power 1. Also decimal point moves here before 6, before non-zero digit. So how many places it goes? 1, 2, 3, 4. So it moves to right. So we consider exponent is minus 4. So floating point representation is minus 1 raised to the power 1, 0 0.6, 10 raised to the power minus 4. In the same way, we can represent other numbers also as floating point representation. So such numbers are stored approximately in computing devices. Okay. So now let us summarize. Fixed point representation is simple but has a very limited range. In floating point representation, mantissa, that is also called significand, determines precision, and exponent determines the scale or range. Internally, calculators often use decimal floating point representation. Calculators uses the digits, decimal digits 0 to 9, while computers use binary floating point representation, means base is 2 here, and digits that are called bits are 0 and 1 for computers. Fixed point representation mostly used in currency and accounting for exact decimal precision, means in accounting and currency we cannot float, we cannot move the decimal point. Floating point representation used in scientific computation involving very large or very small numbers. So this is for today's lecture. Thank you for watching the video. This is my YouTube channel link. Please like, subscribe, comment, and share. If you have any doubt or questions, you can write them in the comments. See you in the next lecture.